Hey everybody, today we're going to be talking about percent composition. Now percent composition is an application of chemistry that comes up often enough that you may have actually seen it referred to and not even realized it.
I'm 40% zinc. My body's 40% titanium. I'm 30% iron. I'm 40% dolomite.
So the first thing we're actually going to talk about is finding the percent composition by mass of a given compound. So the general strategy here is that usually we're not given a total amount of the compound, so we're just going to assume that there's always 1 mole. That way we can just use the molar mass of each element as the mass of the element. It just saves a lot of computation. We're then going to find the total molar mass for each element in the compound. Once we do that, we find the total mass of the compound. And then once we have each part and we have the total mass, we can find the percent composition by mass for each element in the compound. And that's going to be our part over whole times 100%. The general strategy here is that we're basically starting with moles, and we're turning those into grams, assuming that we have 1 mole of compound. We're using molar mass to find grams, and then the grams give us percents. So let's start with this example, find the percent composition by mass of magnesium sulfate. So what I always like to do first is list my elements here. So I see that magnesium is in this, as is sulfur, as is oxygen. So once I have my elements, I need to get their molar masses, because again, I'm going to assume I have 1 mole. That way I automatically know how much mass I have of each. So I've mentioned this before, but you can just find a dynamic periodic table, like the one that I have found right here, ptable.com, and this gives you all the masses you need. So for example, for magnesium, I can see that the molar mass is 24.3 grams per mole. So once I have that information, I can start recording it. So magnesium is 24.3 grams per mole, sulfur is 32.1 grams per mole, and oxygen is 16.0. And as I've said before, that's one you should definitely have memorized by the end of chemistry, because there's enough oxygen in everything. So from there, I also consider how many atoms of each element are actually in 1 molecule of the compound. So here I can see in my compound that there's 1 atom of magnesium, I see 1 atom of sulfur, but I see 4 atoms of oxygen in the compound. And then it's just a matter of simple multiplication. That means there's going to be 24.3 total grams of magnesium, 32.1 total grams of sulfur, but 64.0 total grams of oxygen, because I had to multiply the 16 times 4. And then I find the total mass for 1 mole of this compound, and the total molar mass is 120.4 grams. So what I now have is the part for each element, and I have the whole, the total amount of 1 mole of the compound. And now it's simply a matter of calculating each percent. So I'll do one as an example, but then you should get the idea. So for magnesium, if I see that there's 24.3 grams and 120.4 total, then I can put this in, and that's going to give me a percentage. If you just want to multiply it by 100%, that's fine. So it looks like about 20.2, if I'm sticking to 3 significant figures here, 20.2%. So there's 20.2% magnesium. Finishing with the rest, there is 26.7% sulfur and 53.2% oxygen. Now, an easy way to check this is to make sure these percentages get close to 100%. In this case, it's actually going to be a little over. This adds to 100.1%, but that's just due to rounding error. There's a lot of rounding in doing percent composition, and that's going to be relevant in future examples, so we just have to be mindful of that. So now let's talk about finding the percent composition by mass of calcium nitrate. So a little difference here is we actually have a polyatomic ion that is going to sort of affect like how we count the atoms in this compound. But just like before, I'm starting by listing the elements in the compound. I've got calcium, I've got nitrogen, and I've got oxygen. Using my periodic table, I find the molar mass of each. Calcium is 40.1, nitrogen is 14.0, and oxygen is 16.0. And now I'm going to count the number of atoms. Well, looking at the compound's formula, I only see one calcium. Remember that this subscript 2 refers only to the nitrate, it does not refer to the calcium. So there's one atom of calcium. This is where I have to be careful because since there are two nitrate molecules or nitrate ions for every molecule of calcium nitrate, that means this nitrogen is actually happening twice. So there's actually two nitrogen atoms. And similar idea for the oxygen. Normally there's 3, but it's getting doubled. So there are 6 actual oxygen atoms. Just like before, I multiply to find the total mass of each element in the compound. So for calcium, it's 40.1, nitrogen is 28.0, and oxygen is 96.0, and this gives my total of 164.1. Then I just find the percent composition. Calcium's, I divide 40.1 by the total, which gives me 24.4%. Nitrogen is 17.1%, and oxygen is 58.5%. Those numbers do actually add up to 100%, but again, it's rounding, so sometimes it's going to come out exact with your rounding. Sometimes it's a little off, but there's so much rounding here that we need to just look at that and just keep that in mind as we do these problems. So I hope you could see that. Finding the percent composition is actually pretty straightforward. There's not really a lot of snags or tricks. But the trickier question is, what about going the other way? If I gave you the percent composition, could you figure out how many atoms of each element are in a molecule of the compound? So this actually is a little trickier, but it really just is the reverse of everything we just did. So instead of assuming 1 mole, we're going to assume 100 grams because we're really starting kind of with mass and we're really trying to find molar ratio. So assuming 100 grams makes it easy to work with percents as they're out of 100. We're going to use the molar mass to find the number of moles of each atom and element in 100 grams. And then here's sort of the tricky part. We're going to divide each of these numbers of moles by the smallest number of moles. That will just make our ratio easy to read. You're going to see what I mean by that in the examples to follow. So you should see here that the strategy is really the reverse of what we just did. We're being given percents, we're changing that to grams, and we're using grams to find moles. It's the exact opposite process. So, find the empirical formula for a compound that is 75% carbon and 25% hydrogen. So again, this is by mass, so if you just looked at this, some people might go, oh, that means there's 3 carbons and 1 hydrogen. That's not the way that actually works, because carbon is a much more massive molecule than hydrogen. I mean, every atom is more massive than hydrogen, but carbon is 12 times more massive, so that's why we need to be careful when we do these percentages. So just like before, I'm going to list my elements. I've got carbon and I've got hydrogen. And I need their masses. So again, we're assuming this is sort of 100 total grams. So 75% becomes 75.0 grams. And the hydrogen is 25%. So it's 25 grams. The molar masses, these you should know. Carbon is 12.0 and hydrogen is 1.00. Okay? Now we need to find how many moles there are. So before, when we were going from molar mass to mass, we multiplied. But here, we need to divide. So 75 divided by 12 is going to give me 6.25, and 25 divided by 1 is 25. So notice before, when we were finding percent composition, we did a lot of multiplication. Going backwards and getting the formula, we're going to be doing a lot of division. And now what I'm going to do, this is what I was referring to earlier, the smallest number of moles I have is 6.25. So I'm going to divide both of these numbers by that. That way, the smallest number I'm going to get in my ratio is 1, and that makes it very easy to see what the final ratio is. It's just a little computational trick. So dividing both of those numbers by 6.25, obviously I'm going to get 1 here, but I'm going to get 4 here. This gives me what my empirical formula should be. The empirical formula for this compound should be 1 carbon atom and 4 hydrogen atoms, CH4, which is otherwise known as methane, which is a very fun compound. Now, we call it the empirical formula because technically, since this is a ratio, this could also have been 2 and 8, and it would have been equivalent to these percentages. So technically, the compound C2H8 would have the exact same percent composition. So doing this process doesn't actually tell us if that's happening. It also doesn't give us any information about the structure of the compound. It just literally tells us what the ratio of atoms is of each element in the compound. And that's not a ton of information, not compared to before when we were given the compound and we found percent composition. So here we're just getting the empirical formula. There's not much else we could know without having more information. So let's try the next example. Find the empirical formula for a compound that is 52.14% carbon, 13.13% hydrogen, and 34.73% oxygen. Now, for any of these, if you want to pause the video and see if you get the idea and try it out on your own, and then see if your answer matches mine, that's fine. It's a good idea, in fact, but I'm going to go forward and start this problem. Just like before, we start with our elements. So we have carbon, hydrogen, and oxygen. Again, I'm going to convert those percentages to masses, assuming that I have 100 total grams, so that these percentages are easier. The molar mass of each one, well, now you should be able to say it with me. Carbon is 12.0, and actually I'm using 4 significant digits here because that's what was given me in my problem. So now it's a little trickier. Carbon is actually 12.01 to 4 significant digits. Hydrogen is 1.008, and oxygen is still 16.00. Now again, we find our moles by dividing the mass by the molar mass. So that gives us 4.341 moles of carbon, 13.03 moles of hydrogen, and 2.171 moles of oxygen. Now, as before, we're going to find our smallest number of moles, which is oxygen, and divide every one of these numbers by that number, so that the smallest number in my ratio is 1, and it's easier to see what the relationship is here. So you might be able to eyeball it and guess how this is going to turn out, but let's see what happens. So if we divide 4.341 by 2.171, we get 2.000. Hydrogen, we get 6.002. And oxygen, as obviously, since we're dividing this by itself, we get 1.000. Now, we see here a tiny bit of round-off error. If you're doing these problems and you get mostly zeros here, but just a little difference here, that's probably a rounding error. It's not really likely indicative of anything else. It's only when this first, like this tens digit for now, if that's not 0, then there's probably something else going on, and we're going to see what that looks like in a future example. But basically, we got our ratio here, so it's looking like that there's going to be 1 oxygen, 6 hydrogens, and 2 carbons. This gives us this empirical formula. Now, this is also another classic example of how this process doesn't really tell us much about the compound, it just gives us the actual ratio of the atoms. And the reason why I say this is relevant here is because this is probably going to be the compound that we would normally write as C2H5OH, or ethanol, or ethyl alcohol, because that's a pretty common compound and it has this number of each element in it. But the difference between calling it C2H6O and C2H5OH is a matter of the name indicating the structure of the compound, really. So, however, I can't assume that that information is not present here, so I'm just going to write that that's the empirical formula. So, what about a compound that is 53.73% iron and 46.27% sulfur? So, it's a little more iron than Bender is. He's 30%. So, what are my elements? I got iron and I got sulfur. And you might be thinking, well, this is going to be easier because we're down to 2 elements from 3. Well, let's see what happens here. Again, turning my percentages into masses, and now taking the molar mass of each element, we got 55.85 for iron and 32.06 for sulfur. This gives me 0.9620 moles of iron and 1.443 moles of sulfur. Now, one thing you should immediately notice is, here's my smaller number. This is not a whole number multiple of that. In fact, when we do the division, obviously that first one's going to come out to 1 because it's dividing by itself, but the next one comes out to 1.5. Now, there's no such thing as a empirical formula where a number is not a whole number. So what do I do with this? Well, you should be able to probably predict where this is going. Right now I have a ratio of 1 to 1.5. Since I can't really have a decimal here, and this 0.5 tells me that that's probably not a rounding error, I need to find a way to convert that to the simplest form ratio where both of these are whole numbers. Easiest way I could do that here is multiply numerator and denominator by 2, and that's going to give me a ratio of 2 to 3. So really, this is a 2 to 3 ratio. So the empirical formula is Fe2S3. So this is actually iron 3 sulfide. And last example, find the empirical formula for a compound that is 90.7% lead and 9.33% oxygen. Just good life advice: if you're ever working with anything that's 90.7% lead, you should probably be somewhat careful because it's probably highly toxic, and actually this compound is no exception. So we're starting with lead and oxygen, and again I'm just turning their percentages into masses. And then we find the molar mass of each, and I'm looking, and lead has a molar mass of 207 grams per mole to 3 significant digits, and oxygen is 16.0. Again, that one you should be able to remember by now. Number of moles of each, well, again, dividing the mass by the molar mass, I'm getting 0.438 moles of lead and 0.583 moles of oxygen. Now you should definitely see here that also the smallest number is here, and that this is not a whole number multiple of that. In fact, when I divide both numbers by 0.438, I'm going to get 1.00 and 1.33. So now again, because the tenths place here is not 0, I have a sneaking suspicion that's not rounding error, that's what the ratio is. So I have my ratio of 1 to 1.33, and you should be able to predict what number I can multiply both of them by to make them whole numbers, and I really need to multiply top and bottom here by 3. That's going to give me a final ratio of 3 to 4, which means this compound is actually, it has an empirical formula of Pb3O4. This is a compound known as lead tetroxide, which is a very beautiful orange color. It's also highly toxic and flammable. It's commonly used in pyrotechnics. So this is definitely not a compound you would want to mess around with too much. So anyways, that is our venture into percent composition. I hope that you found this informative, and I will see you guys next time.